Okay, so in this module we will move from essentially inviscid descriptions. Until now we were looking at quasi 1D assumption, we looked at shock waves and expansion waves, and also the variable area ducts. So under quasi 1D assumption, the variation of a compressible flow can be through various driving potentials or drivers. One driver of course is the change of duct area, and a compressible flow happens through the varying area duct, and we spent quite a good amount of time discussing various aspects of this flow, including nozzles, diffusers, and so on. For a large part it is true that we do not have to consider viscous effects because they are quite small, but that is not always correct. So viscous effects have to be considered in real flows. So under quasi 1D assumption, under the 1D flows, the driver for that is friction, fluid friction at the walls, and we are considering 1D flow with friction. So here we do not consider any change in area of the duct. Examples of these kind of flows can be flow through pipes, compressible flow through pipes, gaseous flows through pipes, and this kind of the development of the flow or analysis of the flow was done by Fanno, and it is also named as Fanno flow. So 1D flow with friction or Fanno flow. So what we are looking at is we are looking at a constant area duct. So first we would look at the thermodynamics of these process, and then we will move on to flow the how we would do the flow equations and so on, and these are well described in very good very many books, textbooks of gas dynamics. So several thermodynamic charts and such kind of figures will be taken directly from such textbooks. Here we look at steady flow in constant area ducts. So A is constant, and we are considering flow friction due to viscous forces at the walls, and there is no heat transfer. So the flow is adiabatic. So 1D flow, uniform flow properties, that is quasi 1D assumption, and flow is adiabatic, it is steady. So friction always occurs in the opposite direction of the flow, or it opposes the flow, and this is occurring along the wall. So if you consider a pipe with circular cross section, the force of friction would occur on the lateral surface area. So for a small element, if we can consider this as an element dx, okay, small element dx, or it can be a typical length L, okay, then the lateral surface area is pi d multiplied by dx, and if shear stress on the wall is tau w, then the force is tau w multiplied by pi d dx. So this force acts in the direction opposite to the flow. So once again the analysis of this flow has to be considering all the three conservation equations: conservation of mass, momentum, and energy. Here conservation of mass is straightforward. M dot is constant, so its constant area duct, so rho v is constant, is a constant, okay, because it is a constant area duct. And so we look at now the momentum equation. So in the momentum equation you have forces, you have the flux of velocity is equal to flux of momentum is equal to the forces, that is here it is a pressure forces and the frictional forces. So, here is friction and this is pressure, and we are doing 1D flow. So, we are considering only the x component of these velocities. Now, this can be integrated for a cylindrical volume. So, here the incoming flux is rho 1 u 1 square a is a constant, outgoing is rho 2 u 2 square a, and the pressure forces are P 1 a on the left hand side and P 2 a on the right hand side, while friction force which acts against the flow is pi d tau w dx, and it is an integral 0 to L, because in general tau can vary along the duct. So, this is the factor, now additional factor that comes in the equation. Since we are taking a constant area duct, d is constant. So, pi d can be taken out, a is also constant. So, dividing it by area, you get P 2 minus P 1 plus rho 2 u 2 square minus rho 1 u 1 square is equal to minus 4 by d integral of the shear stress. Okay. So, the major change that happens is in the momentum equation. What about the energy conservation equation? There is no heat transfer occurring over here. So, if you take H1 plus V1 square by 2 is equal to H2 plus V2 square by 2, or it essentially says total enthalpy or total temperature remains a constant. So, if you take the Fanno flow, and first what we shall do is look at the thermodynamic description of Fanno flow as a process and see what we can learn from this description. In fact, almost all aspects of Fanno flow will be covered just by means of one single curve, which is the Fanno curve. How do we get to this curve? It is you consider two equations, which is the mass flux or rho v is constant, and it is given a parameter g. Now, this parameter g will come again and again in the descriptions now, and the other one is total enthalpy, or H plus V square by 2 is a constant. So, total enthalpy is a constant. Now, this can be expressed. So, here given rho v is equal to g, we can express v is equal to g by rho, and this can be substituted in the energy equation, and we get H plus g square by 2 rho square is a constant. So, now if you take this particular equation, then it consists of only thermodynamic variables, along with of course ideal gas equation of state and so on. So, now if we can plot all possible states beginning from an initial point which satisfies these conditions, then such a curve is a Fanno curve. So, Fanno curve is a curve for adiabatic flow through constant area ducts, and it is expressed here in terms of Ts, that is temperature versus entropy, Ts diagram. Now, this is also enthalpy. If you are considering a calorically perfect gas, it is equivalent to enthalpy. So, enthalpy entropy diagram. Okay. So, now if you look at this curve that is represented by these equations, you see it has a particular shape. Now, take note that first, if I start from the upper side of this curve, it actually you can see that the curve slowly drops down in temperature, okay, until it reaches a point. So, here you can see that the entropy is increasing, temperature is decreasing, until a point over here which is the maximum entropy point. Okay, so it is maximum entropy S max. Okay. After this you see that if you consider this particular curve, here I again start from the left side. If I go and I see here that the temperature increases, entropy increases up till the same point which is x max, S max. Now there is a specific reason why we went only in one direction. The reason is that in fact if you plot, so this is all static variables. In TS in case of Fanno curve, the entropy or the stagnation enthalpy remains constant. So let us take it's a straight line, this is H naught equal to constant. So if you look at this, essentially this particular distance describes V square by 2 Cp, or if you take enthalpy it is V square by 2 here. So what you see is this part of the curve which I have described here as is the upper branch. That curve corresponds to small velocities, or it is a for a subsonic flow, while if I take the same corresponding point, if I take it here right here, then V square by 2 is very large. So the bottom branch is a supersonic branch. So this branch is m greater than 1, this branch is m less than 1, and we will soon find out that this point at which the entropy is maximum is actually a critical point which is m equal to 1, and this is an adiabatic flow, and so one should realize that it is not possible. So from here if you take any particular point 1 and a flow happens within a duct where there is friction, essentially you are going to go along this curve, and as you go along this curve, what you find really is that Mach number is increasing, because you get a point which is m equal to 1 here, but from this curve it should be readily understandable that you cannot pass beyond this maximum entropy point. So a subsonic flow can when it happens in a duct with friction, then its Mach number actually increases, and it can increase up to Mach number 1. But if you look at a supersonic flow, similarly if I take another point here which is supersonic here, beginning starting point is supersonic, as the flow happens in the duct its Mach number decreases, but it can decrease maximum to 0.1, and it is not possible to go beyond that. The reason is that it is a maximum entropy point, and if you try to go beyond this particular point, entropy decreases, which is not possible in an adiabatic duct. Entropy has to always increase. But this particular diagram tells you a lot more than this, actually tells you the whole story. So we will go into further details. So these are qualitative curves, and you should actually practice to draw these qualitative curves of Fanno curves, and in the later modules you will learn another one which is Rayleigh curves, and looking at them on looking at problems on described on Fanno curves or Rayleigh curves, TS diagrams gives you a better feel for how to solve them, what are the interrelationships between different variables, because in these problems there is not a single variable that changes. As one parameter changes, all other parameters undergo change. So these diagrams are effective ways to understand the interrelationship between all these variables. So if you draw an HS diagram, then we know how pressure lines look like on a HS diagram. Schematically it is drawn over here. You can, these are basically pressure lines. So, as you go from left to right, pressure actually decreases. Also here on the right hand curve you have different plots where the only parameter that you saw in the Fanno curve was G, which is the mass flux basically, G. So, if you vary G, how does the Fanno line shift? As essentially it shifts in this manner, that as you go from left to right, G decreases, you get lower and lower G. Okay. So, at all these points you have this maximum entropy point, which corresponds to Mach number equal to 1. So, if you look at this curve, immediately what happens to pressure and density will become obvious, because the pressure decreases as you go from left to right. But be mindful, they are not parallel lines. So, they are curved. So, actually if you look at the way, the exact way in which the Fanno line occurs, then in the subsonic branch actually you have a decrease in pressure as you go along the Fanno curve. P decreases in the subsonic branch, but you can notice the supersonic branch is rather steep, and if you draw the pressure lines along this particular curve, supersonic branch, then you will find that pressure will increase, and this corresponding the height over here, this is essentially v square by 2. So, from that you are able to understand that in subsonic flow velocity actually increases in a Fanno flow as the flow goes through a long duct with friction, while in supersonic flow, if the initial velocity entering the duct is supersonic, the velocity decreases. Okay. Now, this is an adiabatic flow. So, for adiabatic flow, H naught is constant, okay, or T naught is constant. Also, the other fact that becomes constant is the value T star, that is the temperature at which it reaches Mach number equal to 1. So, even T star actually is a constant. So, this particular point corresponds to T star, but please do not confuse it with isentropic flows. So, this is a flow in which there is friction. So, friction always introduces entropy, that is why you see that entropy always increases and it reaches a maximum. If a flow occurs through a duct with friction and Fanno flow is considered, then the critical point T star is located here at the maximum entropy point, and T star would correspond to the T star that is obtained in an adiabatic flow, because it is an adiabatic flow. So, in that sense only the T naught T star relationships will be the same, but pressures are completely different. So, P star is not the same as P star in an isentropic flow. So, please bear that in mind and do not confuse between these two. Fanno flow is an entirely different flow where there is change in entropy and entropy increases. Okay. That is an important point. So, now we can completely distinguish between the upper branch, which is a subsonic branch, and the lower branch, which is the supersonic branch. In the subsonic branch, friction causes Mach number to increase and pressure, temperature decreases. So, density also decreases, and velocity increases and there is an increase in entropy. So, whenever there is increase in entropy and it is an adiabatic flow, the stagnation pressure will decrease. This is directly from our first fundamental principles, where we looked at the thermodynamics of process and how stagnation pressure is related to entropy. Okay. So, in an adiabatic flow, if there is increase in entropy, stagnation pressure will decrease. Stagnation pressure decreases across a shock, it also decreases in the case of Fanno curves, okay, or Fanno flows. Now, what happens in supersonic flow? Friction, it causes Mach number to reduce, velocity also decreases, Mach number decreases, and pressure, temperature will increase. Consequently, you have increase in density as well, and P naught, that is P naught will decrease, because even in this case the entropy continues to increase along the supersonic branch. Okay. So, understanding, if you have understood Fanno curves, these curves very well, then you will be in a position to understand Fanno flow very well, because just by means of this particular curve one can completely describe the Fanno flow. So, when a flow is happening, so as point moves from, so initial point 1 here to another point 2 here, represents a flow through a duct of length, corresponding length is L. Okay. So, you can say this is the duct of length L. Now, how we will get to these lengths, and what are the equations that will help us solve them for flow through pipes and so on, we will soon come to it. Here we are discussing thermodynamic aspects of Fanno flows, and just by means of a thermodynamic curve HS or TS diagram, we can know all that is to know about this particular flow. Okay. Now, we have to look at that particular point. So, we are looking at this particular point where there is a maximum of entropy S max, and T naught is a constant. So, constant, what is the condition at which S is equal to S max? Entropy is maximum. What is this particular condition? So, for this we look at the relation TdS equal to dH minus VdP. Here V is specific volume. So, at maximum entropy point, if you look at the neighborhood of a maximum entropy point, essentially it is a maximum. So, ds should be equal to 0. Okay, this is a condition for maxima. So, if you put Ts equal to 0, you get dH equal to Vdp, and from continuity equation, or this is the definition of the mass flux, rho V is equal to G, and G is a constant. So, you can express V, that is the velocity, is G by rho, and 1 by rho is specific volume. So, it is Gv, specific volume. Then the other term which remains constant is the total enthalpy, H plus V square by 2. This V square is now written solely in terms of G and specific volume, G square V square equal to constant, and differentiating this equation we get dH plus G square V dV equal to 0, and so now dH is equal to Vdp, that is from the maximum entropy point. At the maximum entropy point, dH is Vdp. So, now from here we can easily proceed g square this can g square can be written as v square by rho square. So, it can be written as rho square v square, g square is rho square v square, but you also have a v in a specific volume factor over here, and considering all of them together what you arrive at is dp by rho minus v square d rho by rho equal to 0, or v square equal to dp by d rho, and that is happening at this particular point where ds equal to 0 or entropy is constant. So, dou p by dou rho as entropy is constant is nothing but the speed of sound. So, v square equal to the speed of sound or Mach number equal to 1. So, this shows that at the critical point Mach number is equal to 1, or at maximum entropy Mach number is 1, and precisely from the nature of this curve it should be understood that one cannot move from the subsonic branch. So, if you start initially from this point, you are flowing the gas is flowing through the duct and through a length L. Okay. So, L can be varied, it can be having different lengths. So, as you go through different lengths you are getting to different points. So, you have say point 2, you can vary this. So, until you reach this maximum entropy point which is equal to m equal to 1, beyond this it cannot change, okay, because entropy will decrease. Similarly, if you start from a supersonic branch you can go until maximum entropy point, but you cannot go from supersonic to subsonic. So, subsonic to supersonic or supersonic to subsonic flow via a Fanno curve, only via a Fanno curve is not possible, it is limited by entropy. Okay. So, here there are different kinds of Fanno curves that are plotted. This one it is taken from this particular textbook, and these are curves beginning from the same point 1 which is having the same static pressure and temperature, same static conditions, but having different Mach numbers. So, different initial Mach numbers. This, for example, this particular curve belongs in the subsonic branch in G2 as well as in G3. For G3 it is 0.1, G2 it is 0.5, but another curve G1 it is having a supersonic velocity. So, it belongs in the supersonic branch. While the curves on the right show different Fanno curves which start with the same stagnation conditions. So, initial conditions stagnation conditions are the same, but they have different Mach numbers. So, consequently you have different Fanno curves over here. Okay. So, this is how it looks like, and a general understanding, qualitative understanding of how to quickly draw a Fanno curve is very useful in understanding this particular topic and in solving problems also. So, now we come to the point that we want to now look at getting numbers, quantitatively understanding Fanno flow. When trying to do this, we did an initial integration, but we came up with the factor this particular factor 4 by d integral 0 to L tau w dx, because the shear stress in general varies along x direction. So, proceeding this way would be difficult. So, rather under 1D assumption itself with uniform flows, let us look at small lengths dx. So, from an integral kind of an approach we move towards looking at small control volumes with the length dx, we have to just look at the differential form. So, on the left hand side you have dp and plus d rho v square, okay, is equal to now this term is 4 by d tau dx. Okay. Now, rho v square can be differentiated, also considering the fact that rho v is a constant. So, dp plus rho v dv is equal to 4 by tau shear stress dx. Now, we need some way to express the shear stress on the wall. For this we take the definition of coefficient of friction. This is something we can easily borrow. Cf or f is equal to, it is also written as Cf or f, coefficient of friction is tau wall by half rho v square. Okay. Usually f is also not a constant, but it is a slow function of flow condition. So, it does not vary very rapidly, it is somewhat slow in its variation. Okay. So, if you put that, we write then this in terms of rho v square by 2 4 f prime by d. The term f prime is written because soon we will discuss there are two descriptions of this coefficient of friction and friction factor. They are not the same. Coefficient of friction we represent by f prime, while friction factor is represented as f. So, we will soon come to it. So, dp plus rho v dv is equal to minus rho v square by 2 4 f prime dx by d. So, now this can be taken to the left hand side and taken together. Okay. So, you get this particular equation. Now, since coefficient of friction varies very slowly, you can consider an average coefficient of friction defined in this way, f bar is equal to 1 by L integral x1 to x2 f dx. So, and consider that the average friction remains constant. So, this is what has been what I was just now mentioning, is that sometimes many literature describe friction in terms of fanning coefficient of friction, which is the definition of coefficient of friction itself, f prime. But in many places the friction factor, particularly in pipe flows and such kind of descriptions, friction factor is given, which is f is 4 f prime, 4 times Cf, 4 times Cf. So, look at the wordings carefully when you look at literature relevant to Fanno flows, whether they are talking in terms of coefficient of friction or friction factor. So, correspondingly this factor multiplication should be considered. Okay. So, but in general what we understand from here is that we are looking at average coefficient of friction which remains constant. Okay. So, now what about this coefficient? So, here we said we will represent it in terms of coefficient of friction, but we need to know coefficient of friction. For this we can look at several correlations, several relations that are available, that is for laminar flows and turbulent flows. They are expressed in such relations. For laminar flow, of course, this is 64 by Reynolds number, and for turbulent flows also there are various descriptions. For a smooth wall, this is the particular equation, while for walls which have certain roughnesses we have different equations. A suitable equation can be chosen. Also a common chart which sort of depicts all the variations of friction factor or friction coefficient is the Moody chart, where you have the laminar flow and the turbulent flows for different surface roughnesses, because turbulent flows are affected by surface roughness. So, you have all these are available, either if one is doing some of the problems and is using an approach where it can be evaluated analytically, then we can use such analytical expressions or rather relations to get the coefficient of friction, or if one is doing it using calculators and charts, then Moody's chart is available. Okay. But when we are looking at these problems of friction flow through pipes, then we will generally know f would be given and then we would solve the equation. So, that is how most of the textbook problems are given. For applications you can refer to these charts. So, now from here we understood in a qualitative sense what is happening in Fanno flows, and there are differences in how the flow behaves in subsonic flow and supersonic flow, with the point Mach number equal to 1 being the critical point, okay, where entropy is maximum. Now, in the next class what we will look at is look at getting equations in terms of Mach number, so that terms such as pressures, temperatures, change of Mach number can be evaluated in a flow through the constant area duct with friction.